Welcome to the deep dive. Today, we're embarking on a journey into the online encyclopedia of integer sequences. You know, the OEIS. For those of you knee-deep in number theory studies, you already know what an incredible resource this is. Our specific target today, it's a sequence called OEIS A000252. Officially, it's the number of invertible 2x2 matrices modulo n. Now, I know that might sound, well, incredibly specific, maybe even a bit intimidating at first glance, but our goal here, our mission in this deep dive, is to really unpack what that actually means. We want to discover its, frankly, surprising mathematical properties and understand why it's, well, so important in number theory and maybe even beyond. Think of this as your shortcut to getting a good handle on this topic without getting totally swamped in the technical weeds.
It really is a beautifully illustrative sequence, a great example of that profound interconnectedness you find within abstract algebra and number theory. And just to give you a quick feel for it, let's glance at the first few values. For n1, well, it starts simply enough at 1, but then for n2, it immediately jumps up to 6, and it just takes off from there. 48 for nd3, then 96, 480, 288, 2016, 1536 for n8, 38888, 2880, and then for n11, it's all the way up to other 3200. So you can see straight away, these numbers get big, fast. It definitely suggests there's some rich structure underneath.
Takes off is putting it mildly. They absolutely skyrocket. And yeah, that kind of rapid growth often does hint at something pretty fundamental going on. Now, one of the most critical properties, I think, for N000252, and this is a concept anyone studying number theory really needs to grasp, is that it's multiplicative. For those familiar with arithmetic functions, you know how powerful this is. But specifically for N000252, what does that really mean? How does being multiplicative help us, unlock its secrets?
That's a fantastic point, because multiplicative isn't just some dry definition. It's genuinely the key, the shortcut to understanding these kinds of sequences. It means essentially that if you can factor any number n into its unique prime powers, like n equals p1 to the e1 times p2 to the e2 and so on, then the value of the sequence for n, let's call it an, is just the product of the values for those individual prime power components. So an equals a p1e1 times a p2e2, all the way up to a pic. The really profound thing here is how much complexity it strips away. Instead of tackling an directly for every single n, which would be overwhelming, you just need to figure out how it behaves for prime powers. Then you just, multiply those results together. It really lays bare the kind of atomic structure of the sequence.
Okay, that genuinely simplifies things massively. It's like you said, you don't need to build the whole wall at once, just understand the bricks. So, all right, is understanding those prime building blocks is the key. What is the formula? What's the core expression for A000252 when n is just a single prime number, p?
Exactly. The prime case is the absolute bedrock. And for prime p, the formula for AP is, it's surprisingly neat. It's just p squared minus 1 times p squared minus p, p21, p2p. Now, crucially, this number isn't just arbitrary. It precisely represents the order, the size of the general linear group GL2p. Maybe for our listeners, just a quick intuition. GL2p is the group of all possible 2x2 matrices you can invert, where the numbers inside the matrix come from a finite field with p elements. You can think of this finite field as a number system, where arithmetic, addition, multiplication, it all wraps around after p. A bit like clock arithmetic wraps around after 12. So right off the bat, this sequence is deeply tied to counting these fundamental algebraic structures.
That's a perfect connection. It's not just numbers, it's counting something really significant in algebra. Okay, so we've got the prime case nailed down, but like you said, most numbers aren't primes, they're prime powers or products of different prime powers. So how do we extend that elegant prime formula to handle a prime power like p raised to the power e?
Right, but building directly from that prime foundation for prime power p, the formula gets a bit more involved, but it's explicit. It's AP, P12, P plus 1, P4, E3. Now that might look a little daunting compared to the prime case, but remember the multiplicative property we talked about. When you combine this formula with multiplicativity, it becomes incredibly powerful. It essentially gives you all the tools you need to calculate an for absolutely any integer n. You just break n down into its prime power factors, use this formula for each factor, and then multiply all those results together.
It really is amazing how these pieces just click together. And when you put it all together, there's actually a really beautiful and quite concise general formula that summarizes everything. You can write an as n to the power of 4 times a product. And this product runs over all the distinct prime factors p that divide n. The term in the product is specifically 1, 1p2 times 1, 1p. What I find striking about this formula, an 4 product p, 1, 1p, is how clearly it shows the prime factors of n as the the absolute dictators of the sequence's value. They just weave their influence together in this one elegant expression.
And what's truly fascinating, moving beyond just the formulas, is how A000252 serves as this bridge, connecting multiple, seemingly distinct areas of abstract algebra. We mentioned it's the order of GL2P for primes, but AN in general for any n, it's specifically the order of the group GL2ZN. That's the general linear group of 2x2 matrices where your entries are integers modulo n. This is a really cornerstone concept in modular arithmetic and group theory. It's basically counting the ways you can sort of shuffle invertible 2x2 matrices when you're working within one of these finite cyclic number systems defined by n.
Okay, so if I'm getting this right, it's more than just a sequence of numbers. It's literally counting something fundamental within group theory, like a census, as you said, of these specific matrix structures modulo n.
Precisely. A census is a good way to put it. And the connections go even deeper. It links to what might seem like a completely different structure. This sequence, AN, also represents the order of the automorphism group of the direct product of two cyclic groups of order n. We usually write that as Cn cross CNN. Now, automorphism group sounds a bit technical, maybe, but what it boils down to is that the sequence is counting the number of structural symmetries within these specific kinds of groups. It's counting how many ways you can rearrange the elements of CnXCn while keeping its core group structure intact. It just highlights how tightly interwoven these different mathematical contexts really are. Invertible matrices, modular arithmetic, group symmetries, all tied together by this one sequence.
That is a truly remarkable web of connections, deep mathematical links. It really speaks volumes about how interconnected these abstract ideas can be. And speaking of interesting little details, there's a fun, specific pattern that just pops out of the sequence, almost like a little mathematical quirk. Apparently, for any n that's greater than 2, the value an is always divisible by 48. It's like the sequence comes with this built-in guarantee. Divisible by 48. Is there an intuitive feel for why that particular number 48 emerges?
It is a delightful observation. And it's actually a beautiful direct consequence of those prime power formulas and that multiplicative nature we keep coming back to. You see, for n2, n must have a prime factor of either 2 or 3, or it must be a higher power of 2, like 4 or 8, or maybe even involve both 2 and 3, like 6 or 12. And when you look at the formulas, especially for a2 and a 3, well, when you crunch the numbers, the factors required for 48, which is 16 times 3, just consistently appear. For instance, A2, 6, A3, 4, 20, and 4, A4, 96. Good divisibility holds. It's a really satisfying example of a larger pattern emerging directly from the properties of its prime components.
That makes perfect sense. The prime building blocks dictate the rules for the whole structure. Okay, and looking at the bigger picture again, A000252 doesn't exist in a vacuum, right? It must connect to other important sequences in the OEIS landscape.
Oh, absolutely. It's very well connected. For instance, AN can be expressed quite elegantly as a product of two other quite significant sequences. It's A000006 multiplied by phi n. Now, for listeners familiar with Euler's totient function, phi n that counts numbers less than SL prime to n, that's the famous OEIS A000007, and A000006, that sequence represents the order of SL2ZAN. That's the special linear group of 2x2 matrices modulo n. The special part means we're only counting the invertible matrices whose determinant is exactly 1 modulo n.
Okay. So the general linear group size, which is our A000252, is basically the size of the special linear group times Euler's totient function. That's a very neat identity. It really clarifies the relationship between those two important matrix groups, GL2ZN, counting all invertible ones, and SL2ZN, counting just those with determinant 1. Gives a fuller picture.
Precisely. It shows how these matrix groups are structured and related to each other, and how that structure connects back to fundamental number-theoretic functions like phi 10.
This is all incredibly rich, mathematically beautiful, but let's be honest, maybe sounds a bit abstract to some listeners. Has this sequence or the group theory behind it ever surprised you by, like, cropping up in an unexpected, maybe more real-world context? Does it connect outside pure math?
That's a really crucial question. Because yes, abstract math often forms the bedrock for very practical things. And this sequence, or rather the group GL2ZN that it counts, definitely has practical relevance. One particularly interesting place it shows up is in cryptography. Specifically, when you analyze the security properties of the Hill cipher. The Hill cipher is a classical cipher, a type of polygraphic substitution cipher. Basically, it scrambles blocks of letters using matrix multiplication modulo, some number, usually 26 for the alphabet. Now, to make this cipher work, to be able to decrypt the message, the matrix you use for encryption must be invertible modulo n. So understanding the number of such invertible matrices, which is exactly what our sequence AN counts, is absolutely fundamental to analyzing the Hill cipher security. It determines the size of the possible key space. If the matrix isn't invertible, you can't get the original message back. So, yes, counting matrices modulo n directly impacts how we think about the security of certain communication methods. It's a nice bridge from number theory to applied cryptography.
Wow, that's a fantastic example. It makes the abstract suddenly very tangible, very important. Securing communication. It really makes you wonder what other cryptographic systems might rely on similar deep number theoretic ideas. Okay, and thinking about wider views again. Mathematicians don't just look at individual terms, right? They also study the long-term behavior. What about asymptotics, or sums? How does A000252 behave when n gets really large?
Right. Looking at the bigger picture, the long-run behavior reveals even more structure. For instance, if you look at the sum of the first n terms, sum k1 to nik, this sum grows very predictably. It behaves asymptotically like c times n to the power of 5 divided by 5. Here, c is actually another interesting constant, listed in the OEIS as A330523. It's approximately 0.535896. This asymptotic formula tells us just how incredibly fast the cumulative sum of these terms grows. It really emphasizes that explosive growth we saw in the first few terms.
Right, so as n heads towards infinity, the total sum follows this very specific n5 curve. It truly skyrockets.
It really does. And perhaps even more counterintuitive, if you look at the sum of the reciprocals, sum n, 1an, you're adding 1 over 1 plus 1 over 6 plus 1 over 48, and so on. These terms get small very fast, and this infinite sum actually converges. It settles down to a specific finite value. It's approximately 1.205901. The fact that this sum converges tells us something quite deep about how sparsely the large values are distributed, or rather how quickly the terms grow. These kinds of analytical properties looking at sums and asymptotics reveal yet another layer of the rich structure hidden within these integer sequences. It connects number theory to analysis.
Okay, well, we've certainly taken a comprehensive deep dive into OEIS A000252 today. We explored its definition, counting those invertible 2x2 matrices modulo n. We uncovered its crucial multiplicative nature. We dissected the formulas for primes and prime powers, saw how they build everything up. And we really appreciated its profound connections, linking it to different areas of group theory like GL2, ZN, and automorphism groups. We even touched on a very concrete application in cryptography with the Hill cipher. It really is a fantastic testament to the interconnectedness and, frankly, the elegance of mathematics.
Absolutely. This journey through A000252 really underscores how these sequences, which might seem purely abstract at first glance, can reveal these deep universal mathematical structures. And as we saw, they can even underpin practical applications like securing digital information. So maybe a final thought for everyone listening, especially those deep in number theory studies. As you continue exploring, consider this. What other sequences in the OEIS, maybe ones that look even simpler on the surface, might be hiding similar incredible depth? What surprising connections are just waiting there for someone to uncover them? The OEIS is just brimming with these kinds of mathematical mysteries. Each one is a potential deep dive, and each really speaks to the endless fascination of numbers and their patterns.